Hello everyone, my name is Savehshemshaki. Today I'm going to talk to you about our paper, A Receding Horizon Battery Shortage Prevention Control Strategy for Electric Unmanned Vehicles. My supervisor, Dr. Lucia, and I have done this work from Concordia University. The outline of this presentation is: first, I'll explain the scenario behind this work, then we'll see how the problem is formulated. After that, the way our novel strategy is proposed, and finally, we'll see some simulation examples. The scenario of this work is we consider electric unmanned vehicles powered by a limited energy battery and moving in a two-dimensional planar environment. The EUV has a battery manager capable of preventing energy shortage. As it is illustrated in the figure, the EUV needs a trajectory to track, so the vehicle is equipped with a reference generator to provide its trajectory. The EUV is subject to physical limitations, which are bounded states and acceleration constraints. Now, to start formulating our problem, we need to know the EUV's model. This class of vehicle is described by constrained discrete time linear model. The state space representation is shown here. The EUV is subject to the following bounded states and acceleration constraint, and it is also subject to the bounded disturbances. To have a better perspective on our problem, we need to consider some assumptions. First, we consider that if the initial position and the desired destination are given P0 and PD in this figure, the EUV's reference generator provides the trajectory that vehicle need to track as a sequence of NP waypoints that are these points that you can see here, and we should know each of these two successive waypoints has a maximum distance delta with the other one. Then we need to model the battery discharge rate, which is presented here. And as you can see, it is proportional to the EUV's acceleration magnitude. It is worth mentioning that this battery discharge model is an approximation of the actual battery discharge function, which generally depends on several other parameters. You can check the references if you are interested in. However, this model that we present here accurately describes the battery discharge rate as a function of its predominant factor, which is the vehicle acceleration magnitude. And we also assume that a battery manager module can override the input constraint by imposing, whenever necessary, an arbitrary but admissible maximum acceleration profile, UBM of t. The control problem that we are facing here is, regardless of disturbance realization, input and states constraint, EUV has two objectives. The first objective is it should sequentially track the waypoints that are provided by the reference generator. And the second objective is to prevent energy shortage while following the references. So we find the model predictive control represent a natural solution. So we propose a novel control architecture which presented in this figure. This control framework consists of two main units. The first one is a set-theoretic model predictive controller to satisfy the first objective, which is sequentially tracking the waypoints. And the other unit is a battery manager module that fulfills the second objective, which is preventing energy shortage. As you can see here in the figure, the planner provides a sequence of waypoints to battery manager and Set-Theoretic MPC. Set-Theoretic MPC is responsible for reaching each waypoint received by the planner. And EUV sends its current states to the Set-Theoretic MPC to let it calculate the next control law for EUV. And the battery manager, given the waypoints and the state of charge of EUV and also the desired profile, it defines the acceleration input constraint of the vehicle UBM of t. So we'll see how the set-theoretic MPC tracking works here. It has two phases, the offline and the online phase. In the offline phase, we compute a stabilizing state feedback control law and the associated RCI region, which is this green green polyhedron that you can see in the figure. After computing the RCI region, we start from that region to build a sequence of n robust one-step control level set. As you can see in the figure, these green polyhedrons are showing the family of one-step control level set. As it is evident here, the union of these robust one-step control level sets represent the controller's domain of attraction. In this figure, this domain of attraction is this blue polyhedron. In the online phase, we use the Set-Theoretic MPC to switch between waypoints. So in this phase, first we should find the minimum set that EUV is belong to, because we need the one that is closer to RCI region. Then we check if it is in the RCI region, so it can switch its waypoint, and we need to set the next waypoint as a new equilibrium point. When it is not in the RCI region, it means that it should move within one-step controllable set by solving this optimization problem. What is worth mentioning here is waypoint switching must be done when EUV is in RCI region, and the necessary condition for waypoint switching is, as you can see here, the next family of one-step controllable sets contains the previous family's RCI region, so our controller's recursive feasibility is guaranteed. Before designing the battery manager unit, to prevent battery shortage during the reference tracking, we need to have a prediction model for energy usage. Let's consider a finite set of admissible acceleration constraints profile, which is this U set. This set contains admissible acceleration constraints that satisfy this condition that U1 is subset of U2 and so on, so that at each sampling time the battery manager can arbitrarily impose an arbitrary acceleration constraint UBM of t, which is in U set, and the control law which the set-theoretic MPC compute at each sampling time is in this UBM of t. So for each constraint set UL in U set, a different worst case energy consumption can be defined, as you can see here. In this formula, alpha bat is a scalar coefficient whose value is a function of the specific battery model. Norm of UL is the maximum acceleration norm that in worst case U of t computed by set-theoretic MPC can be equal to this one. NL is the number of one-step controllable set for the associated UL. The result of this formula, the result of this formula is the energy that EUV consumes to track one waypoint in the worst case scenario. And to see how much energy it consumes to track all the NP waypoints, this energy consumption should be multiplied by NP, as it is shown in this equation. By knowing the energy usage model for reference tracking by set-theoretic MPC, now we can design the battery manager. Its main task is find an admissible input constraint profile, UBM of t, such that EUV can reach the desired destination while minimizing the desired cost function. So BM must be able to find generic time evolution for UBM of t, which is this equation. This equation shows the time and the number of waypoints, this and L, in which the input constraint set level L is active. To find this and L and then find the conservative acceleration profile UBM of t, we should find the solution for the following linear programming problem. A possible multi-objective choice for J, which is function of N1 to NL, is this equation, in which we define a weighting parameter, gamma and beta, for the time that EUV takes, this one, to track, and for energy, this one, that EUV consumes to track. Depending on the gamma and beta, three different cost functions can be defined and solved by Battery Manager before it starts operating online. First cost function is minimum time. With this value of gamma and beta, it minimizes the number of discrete time instants needed to reach the target. As you can see here in the figure, it is the profile that is shown by green. The second one is minimum energy. With this value of gamma and beta that is illustrated here, it minimizes the total amount of energy needed to reach the target, as it is shown by red profile in this figure. And the other cost function is multi-objective one, in which both gamma and beta are greater than 0, and it will be used to find the best compromise between the minimum time and the minimum energy solution, which is this blue profile in the figure. The cost functions are very conservative profiles for EUV, these cost functions that we saw together. So in the online phase, the offline conservative acceleration profiles that are found by the BM at t equals to 0 can be improved or can be changed without affecting the set-theoretic MPC feasibility. For changing the cost function, it has been shown that the tracking controller preserves recursive feasibility regardless of any admissible change in the acceleration constraint, so that at any t, any admissible cost function j can be imposed. It can be multi-objective one, minimum time, or minimum energy. To improve the same cost function, we can calculate the predicted remaining charge by using this formula. By using this formula, we should subtract the predicted consumed charge from the initial state of charge, and we will have then this predicted remaining charge. On the other hand, we can calculate the actual state of charge by using this formula and using the inputs u of t at each t. If the actual state of charge is greater than the predicted one, it means that we have more energy than we expect to have. So we can resolve the main optimization problem and use the current state of charge instead of the initial state of charge. And finally here, we present a simulation example that shows the effectiveness of the proposed control technology. In the simulation, a UEV is described by double integrator model subject to different states acceleration constraints and disturbances as they are represented here. The EUV's objective is implemented, the EUV's objective in this example is to reach the target destination in the minimum possible time. The BM algorithm is implemented considering 4 possible levels of acceleration as it is illustrated here. By considering 4 levels of acceleration constraint and calculating the norm of each of these 4, we can have an associated worst-case energy consumption profile for a single waypoint tracking at each level. For example, when having a norm of UL as a maximum acceleration, this one, the EUV will consume this value to track a single waypoint. In this simulation, 2 scenarios are simulated. The first one is the BM optimization problem is never online recomputed. We call it frozen. The second one is that the BM optimization problem is periodically solved every 50 waypoints. We call it updated. Let's take a look at this figure in bottom. At t equal to 0, the battery manager predicts that using an acceleration profile equals to 14.14 until t equals to 1.9, and then the profile equals to 9.89 for the rest of the t. This represents a conservative solution that predicts the vehicle will reach the destination at t equals to 586 seconds. This profile is shown in this red dashed line. Then we are also showing when it is updated at t equal to 1.9, when the 50th waypoint is reached. At this time, BM realizes that the current state of charge is greater than the predicted one, as you can see here. So the BM optimization can be resolved, and the same reason applies to all the other time instants when the optimization is resolved and the profile is updated. And the updated profile is also shown in the green here. Furthermore, you can see here the final state of charge for each scenario, the updated scenario and the frozen scenario. In this figure, in this one, you can see that by using the updated profile, the EUV is capable of reaching the destination at t equals to 383 seconds. And this red car here shows when the vehicle is at the same time in the first scenario, it is busy with the trajectory tracking and it hasn't reached the goal yet. This figure also shows that the acceleration vector norm is sometimes lower than the maximum allowed value. As a consequence, EUV isn't using all the predicted amount of energy, and that's the reason why we can't get a better profile by resolving the optimization problem. In conclusion, in this paper, we have proposed a solution to deal with the battery shortage problem for constrained electric vehicles. The solution takes advantage of peculiar properties of set-theoretic MPC control paradigm to couple the battery manager problem with a set-theoretic based tracking controller. The proposed battery manager can offline find a conservative acceleration constraint profile that can be online improved using the current information about the battery state of charge. Future work will focus to extend the proposed solution for a more complete nonlinear model of a car. Thank you for your attention to this presentation.